Hello and welcome to Bedtime Science. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of science and the universe. It helps the channel grow and lets more curious minds find their way here. And I'm always fascinated to know where people are listening from. So if you feel like sharing, leave a comment telling me where in the world you're watching or listening tonight. Maybe you're in a quiet apartment somewhere in Tokyo, a late-night train in London, a small town in Canada, or perhaps under a clear sky somewhere far from city lights. Wherever you are, the remarkable thing is that the same physical laws are unfolding around you right now. The same gravity that keeps the moon in orbit is gently holding you to the earth beneath your feet. The same electromagnetic forces that power distant stars are quietly running through every device around you. And the same atoms that once formed ancient stars are now part of the world you're sitting in. Physics often feels like something distant. Equations on a blackboard, complex diagrams in textbooks, or the work of famous scientists whose names appear in history books. But in reality, physics is something far more intimate. It is the hidden story of why anything behaves the way it does at all, why objects fall, why light travels through space, why time seems to flow forward, why matter exists, why the universe itself has structure rather than chaos. For thousands of years, humans have looked at the world around them and asked quiet questions. Why do the stars move across the sky each night? Why does a stone dropped from a hand always fall downward? Why does fire give warmth? And why does the wind move the clouds? What we now call physics grew slowly from those simple observations, not all at once, and not through a single discovery, but through centuries of curiosity shared across many cultures and civilizations. Philosophers, astronomers, mathematicians, engineers, and experimenters all contributed pieces to a puzzle that is still far from complete. Some of those names are well known, others are less familiar but just as important. Together they helped reveal something extraordinary. That beneath the immense complexity of the universe lies a set of patterns so reliable that they can be written down as laws of nature. But physics is not just a list of those laws, it is a way of thinking, a way of asking questions, a way of searching for hidden simplicity inside overwhelming complexity. And sometimes the answers physics uncovers are stranger than anything we might have imagined. Particles that behave like waves, empty space that isn't truly empty, time that slows down when objects move faster, black holes that bend space itself. The deeper physicists look, the more the universe seems to reveal layers beneath layers, each one more subtle than the last. Tonight, we're going to explore what physics really is, not just the discoveries, but the ideas behind them, the ways scientists learned to see patterns where none were obvious, the surprising principles that guide the motion of planets, the behavior of atoms, and perhaps even the structure of reality itself. We'll move slowly, gently, and thoughtfully through the history and philosophy of physics, from early observations of nature to some of the most profound theories scientists are exploring today. So wherever you are in the world tonight, settle in, relax, and let your mind wander a little. Because the story of physics is in many ways the story of how humans learned to understand the universe we find ourselves in. And as it turns out, that story is far stranger, deeper, and more beautiful than it first appears. If you pause for a moment and look around the room you're in right now, something quietly remarkable becomes apparent. Everything behaves in a predictable way. A glass resting on a table stays exactly where it is. If you were to nudge it gently, it would slide across the surface in a smooth and understandable motion. If you pushed it too far, gravity would pull it downward and it would fall toward the floor. Light from a lamp travels in straight lines until it reflects from the walls. Sound moves through the air at a steady speed until it reaches your ears. Nothing behaves randomly. The universe, at least on human scales, seems to follow rules. And that observation leads to one of the deepest questions physics has ever asked. Why? Why should the universe have rules at all? Why does matter behave consistently from one moment to the next? Why does gravity always pull downward on Earth rather than sometimes sideways, or occasionally upward just to keep things interesting? For most of human history, these questions were not framed in terms of physics. Instead, they lived inside philosophy, mythology, and early attempts to understand nature. People noticed patterns in the world long before they had any mathematical tools to describe them. In ancient Greece, more than 2,000 years ago, thinkers began asking whether nature might operate according to hidden principles. One of these thinkers was Heraclitus, who lived around 500 years before the Common Era. Heraclitus believed the universe was constantly changing. According to him, the world was defined by transformation. Rivers flowed, fire burned, seasons turned, and nothing ever remained exactly the same. But even within that constant change, Heraclitus believed there was an underlying order he called the Logos. This was not a physical law in the modern scientific sense, but it was an early attempt to describe the idea that the universe might have an organizing logic. A few generations later, another group of thinkers proposed something even more radical. Democritus and the early atomists suggested that everything in the universe might be made from tiny indivisible particles called atoms. According to their view, the endless variety of objects in the world came from different arrangements of these fundamental pieces. They imagined atoms moving through empty space, colliding and combining in countless ways. At the time, this idea was purely philosophical. There were no microscopes capable of revealing atoms, and no experiments that could prove such particles existed. But the concept contained something important. It suggested that complex phenomena might arise from simple, underlying rules governing basic building blocks. That idea would eventually become central to physics. For many centuries after Democritus, however, a different picture of nature dominated intellectual life. The philosophy of Aristotle shaped scientific thinking throughout the ancient world and deep into the medieval period. Aristotle believed that objects moved according to their natural tendencies. Heavy objects, in his view, sought their natural place at the centre of the world, which explained why stones fell downward. Fire, by contrast, moved upward toward the heavens, because it was associated with a lighter element. This framework described observations reasonably well on the surface, but it was not based on measurement or experiment. It relied on logical arguments and philosophical reasoning rather than systematic testing. And yet, even within the long shadow of Aristotelian thinking, a few scholars began noticing problems. During the medieval period, several thinkers quietly questioned whether motion worked the way Aristotle described. Among the most interesting of these were Jean Buridan and Nicole Oresme, scholars working in 14th century Europe. Jean Buridan, who taught at the University of Paris, developed a concept he called impetus. Buridan proposed that when an object is thrown, the motion continues because the object carries an internal property imparted by the thrower. This impetus gradually fades due to resistance from the surrounding air. While not identical to modern physics, This idea strongly resembles what we now call momentum. Momentum is the quantity that combines an object's mass with its velocity, describing how difficult it is to stop its motion once it is moving. Buridan did not write equations for momentum, but his reasoning hinted at the same underlying principle. Nicole Orazem expanded on these ideas and explored ways to represent motion using graphical methods. In some of his work, Orazemi plotted quantities in ways that resemble early coordinate graphs, centuries before the formal development of analytic geometry. These medieval scholars rarely appear in popular science stories, but their ideas helped loosen the intellectual grip of Aristotelian physics. They showed that motion might follow rules that could be analysed logically and perhaps even measured. What makes this history fascinating is that the idea of natural laws did not appear suddenly. It emerged slowly as generations of thinkers struggled to explain the patterns they saw around them. At some point, humans began to suspect something extraordinary. The universe might not just behave consistently by coincidence. It might follow universal principles that operate everywhere. The same rules governing the motion of a falling stone might also apply to the movement of the moon. The same laws shaping a candle flame might apply to distant stars. Today this idea seems obvious because we grow up learning about physical laws in school. Gravity pulls objects toward Earth. Light travels at a constant speed in empty space. Energy cannot be created or destroyed. But none of these concepts were obvious at the beginning. They had to be discovered, one insight at a time. What physicists eventually realized is that nature appears to operate through a network of deep patterns. These patterns are consistent enough that they can be expressed mathematically and tested through experiment. And once discovered, they often apply far beyond the situations where they were first observed. For example, the gravitational attraction between objects follows a precise mathematical relationship. If you double the distance between two masses, the strength of their gravitational pull decreases according to a specific rule called the inverse square law. This relationship holds true whether the masses involved are two stones on Earth or two stars separated by enormous distances in space. The same pattern repeats across scales ranging from everyday life to the structure of galaxies. In this sense, physics is not just the study of objects or forces. It is the search for patterns that remain stable across time, space, and circumstance. Physicists look for regularities hidden beneath the complexity of the world. Why do planets move in predictable orbits? Why does heat flow from warmer objects to colder ones? Why do atoms combine into molecules in particular ways? Each of these questions reflects the same underlying curiosity. Somewhere beneath the surface, there must be principles shaping how matter and energy behave. The remarkable discovery of modern science is that these principles can often be expressed with surprising simplicity. Complex phenomena emerge from relatively straightforward rules, and once those rules are uncovered, they allow us to predict the behavior of systems we have never seen before. A scientist studying the motion of falling objects on Earth can write equations that also describe the trajectories of satellites orbiting the planet. A physicist investigating the properties of atoms can explain the colors of distant stars. The same laws apply everywhere. That realization may be one of the most astonishing discoveries humanity has ever made. The universe is not chaotic in the way it might have been. It is structured, ordered, governed by patterns that appear consistent across vast stretches of space and time. Why that should be true remains one of the deepest mysteries physics continues to explore. Some physicists suspect that these laws emerge from deeper symmetries within the structure of reality itself. Others believe the laws may arise from underlying mathematical frameworks we've only begun to understand. And some philosophers have suggested that the existence of laws may be tied to the conditions required for complex structures, including life, to emerge. But regardless of the ultimate explanation, the search itself defines what physics is. Physics is the patient effort to uncover the rules that quietly govern the universe. Rules that shape the motion of galaxies. Rules that determine how atoms interact. Rules that guide light across billions of light years of empty space. And the most remarkable part is that those same rules are unfolding right now in the room where you're sitting. The light reaching your eyes obeys them. The air you breathe follows them. Even the atoms in your body, once forged inside ancient stars, move according to the same principles that guide the motion of distant planets. All of it connected by patterns that physicists have spent centuries trying to understand. And the deeper we look, the clearer it becomes that these patterns are not random accidents. They are clues. Clues pointing toward the hidden architecture of reality itself. Long before telescopes, laboratories, or chalkboards filled with equations, human beings had already begun doing something very scientific. They watched. They noticed that the world did not behave randomly. Certain events repeated again and again with remarkable reliability. The sun rose in the east every morning and set in the west every evening. The moon grew from a thin crescent into a bright circle, and then slowly faded away again in a steady rhythm that took about 29.5 days. The seasons turned in a cycle lasting a little more than 365 days. These repeating patterns were impossible to ignore. Even without modern instruments, ancient observers could see that the sky itself seemed to follow a schedule. Night after night the stars wheeled slowly across the heavens in predictable arcs. Constellations returned to the same positions at the same time each year. Bright wandering lights, which we now know as planets, drifted across the background stars in ways that were complicated but not completely chaotic. Recognizing these patterns was one of the first steps towards science. The ancient Babylonians, working thousands of years ago, kept careful records of planetary movements and lunar eclipses. Their clay tablets contain lists of observations that stretch across generations. By studying these records, Babylonian astronomers were able to predict eclipses and planetary positions with surprising accuracy. They did not necessarily understand the deeper reasons behind these motions, but they understood the patterns, and that was enough to make useful predictions. Later, in the Greek world, astronomers began building mathematical descriptions of these patterns. One of the most influential figures in this effort was Hipparchus, who lived around 150 years before the Common Era. Hipparchus carefully measured the positions of stars and planets, and created one of the earliest known star catalogues. His observations were extraordinarily precise for the time. By comparing measurements taken years apart, Hipparchus discovered something subtle but important. The position of the equinoxes slowly shifted relative to the stars over centuries. This phenomenon is now called the precession of the equinoxes. It occurs because the Earth's rotation axis slowly wobbles, like a spinning top that is beginning to tilt. The full cycle of this wobble takes about 26,000 years. Hipparchus did not know the cause of this motion, but he identified the pattern through careful measurement. His work demonstrated that even slow and subtle movements in the heavens could be detected if observations were precise enough. A few centuries later, another astronomer attempted to assemble all known knowledge of the cosmos into a comprehensive system. This astronomer was Claudius Ptolemy, who lived in Alexandria during the 2nd century of the Common Era. Ptolemy wrote a monumental work called the Almagest. In it he described a detailed mathematical model designed to predict the motions of the sun, moon, and planets. According to Ptolemy's model, Earth sat motionless at the centre of the universe. The planets moved along circular paths called deferents, while also travelling around smaller circles called epicycles. It sounds complicated, and in truth it was. But the remarkable thing is that Ptolemy's system worked. By carefully adjusting the sizes and speeds of these circular motions, astronomers could predict planetary positions with reasonable accuracy. Sailors could navigate using the stars. Calendars could be refined. Eclipses could be anticipated. What makes this especially interesting is that Ptolemy's model was not physically correct. The Earth is not the centre of the universe, and planets do not move along epicycles attached to crystalline spheres. Yet the mathematical structure of the model captured the observable patterns well enough to make predictions. This reveals an important concept that still exists in modern science. A scientific model does not always need to explain the ultimate cause of a phenomenon in order to be useful. Sometimes it simply needs to describe the pattern accurately enough to predict what will happen next. In other words, models can work even when the deeper truth remains hidden. While Greek astronomers were developing their models around the Mediterranean, scholars in other parts of the world were making equally sophisticated observations. In India, the mathematician and astronomer Aryabhata wrote a remarkable treatise called the Aryabhatiya around the year 500 of the Common Era. Aryabhata proposed that the apparent motion of the stars across the sky could be explained by the rotation of Earth itself. In his framework, Earth turned on its axis while the stars remained relatively fixed. This was a profound insight. Today we know that Earth rotates once every 23 hours, 56 minutes, and 4 seconds relative to the distant stars. That rotation creates the daily motion of the heavens. Aryabhata also calculated the length of the year with impressive accuracy, estimating it as approximately 365 days, 6 hours, 12 minutes, and 30 seconds. The true value is very close to this. Again, what stands out in these achievements is not simply intelligence or creativity. It is careful observation combined with pattern recognition. When observations accumulate over long periods, patterns emerge. And once patterns are recognized, they can be described mathematically. This combination of observation and measurement gradually formed the earliest scientific framework. Observation provides raw information about the world. Measurement turns those observations into numbers that can be compared, analyzed, and refined. Together they allow patterns to become visible. Imagine watching waves reach a shoreline. At first it might seem random, but if you observe carefully, you notice a rhythm. Waves arrive at regular intervals. Their heights vary within a predictable range. With enough data, a pattern becomes clear. Ancient astronomers were doing something very similar, except their shoreline was the sky. They watched the movements of celestial objects for years, sometimes for decades, recording positions relative to fixed stars. Slowly, patterns revealed themselves. These patterns did not immediately produce the laws of physics we know today. That would take many centuries more. But they did establish a powerful idea. Nature is not chaotic. The universe follows regular, repeating behaviors that can be discovered through patient observation. Once this idea takes hold, it changes the way people think about the world. Instead of asking why events occur in purely philosophical or mystical terms, observers begin asking measurable questions. How long does it take for a planet to return to the same position in the sky? How often does the moon pass through its phases? How does the brightness of a star change over time? Each of these questions invites measurement, and measurement produces data. Over time, patterns extracted from that data become the foundation for deeper understanding. Eventually, scientists realized that many of these patterns could be expressed using mathematical relationships. For example, later astronomers would discover that planetary motion follows precise rules connecting orbital distance and orbital period. The farther a planet lies from the Sun, the longer it takes to complete one orbit. This relationship was eventually described mathematically in what became known as Kepler's third law. The pattern was always there in the sky. It simply required careful observation to reveal it. The early history of astronomy and natural philosophy shows something important about the nature of physics. Physics does not begin with equations. It begins with noticing that the universe behaves consistently enough to be studied. The rising and setting of the sun, the turning of the seasons, the shifting paths of planets, each repeating pattern whispers the same message. There is order here. And if there is order, then perhaps there are rules behind it. Recognizing those patterns was the first step in the long journey toward discovering the laws of nature that govern the universe today. For many centuries, the way people understood motion seemed perfectly sensible on the surface. If you pushed a cart, it moved forward. When you stopped pushing, it gradually slowed down and eventually came to rest. If you threw a stone through the air, it travelled for a short distance and then fell to the ground. From these everyday experiences, the ancient philosopher Aristotle concluded that motion required a continuous cause. According to Aristotle, objects moved only when something actively pushed or pulled them. Once that push stopped, the motion should also stop. This explanation appeared reasonable because it matched ordinary observation. When a wagon rolled across a dirt road, friction from the ground and air gradually slowed it down. Aristotle interpreted this slowdown as evidence that motion itself needed constant encouragement. For nearly 2,000 years, this view shaped how scholars thought about the physical world. But over time, a few curious thinkers began to notice that something about this explanation felt incomplete. One of the most important figures in this quiet intellectual shift was a 14th century scholar named Jean Buridan. Buridan taught at the University of Paris and spent much of his career studying motion and the behaviour of projectiles. Instead of accepting Aristotle's explanation without question, he carefully considered what happens when an object is thrown. When someone throws a stone, the hand only touches the stone for a brief moment, yet the stone continues moving long after it leaves the thrower's hand. If motion truly required constant pushing, what exactly was pushing the stone while it sailed through the air? Aristotle had proposed that the surrounding air itself moved behind the projectile and continued to push it forward, but Buridan found this explanation unsatisfying. Instead, he suggested a different idea. When an object is set in motion, it received an internal property that carries the motion forward. Buridan called this property impetus. According to his reasoning, the act of throwing transfers impetus into the stone. That impetus keeps the stone moving until resistance from the air and gravity gradually reduces it. Although Buridan did not use modern mathematical language, his idea closely resembles the concept of momentum used in physics today. Momentum describes the quantity of motion possessed by an object. It depends on two things: the object's mass and its velocity. In modern terms, the relationship is written as momentum equals mass multiplied by velocity. Buridan never wrote that equation, but the logic behind his idea was remarkably similar. He recognized that motion could persist without continuous pushing, provided the object carried something with it from the original action. This was a subtle but profound shift in thinking. Motion no longer needed a constant external cause. Instead, motion could continue naturally once it had begun. Another thinker who challenged traditional ideas about motion was the Italian mathematician Giambattista Benedetti, working during the 16th century. Benedetti studied falling objects and questioned Aristotle's claim that heavier objects fall faster than lighter ones. Aristotle believed that the speed of falling depended directly on weight. A stone 10 times heavier than another should fall 10 times faster. But Benedetti noticed something strange about this claim. If two objects are dropped from the same height, the difference in their fall times is often surprisingly small. In many cases, they appear to land almost simultaneously. Benedetti reasoned that the rate of falling must depend on something other than simple weight. He proposed that objects of the same material but different masses should fall at similar speeds, because their densities remain constant. This insight moved closer to the modern understanding that, in the absence of air resistance, all objects near Earth's surface accelerate downward at the same rate. That acceleration is approximately 9.8 meters per second every second. In other words, an object starting from rest gains about 9.8 meters per second of speed during each second of free fall. These ideas set the stage for one of the most famous scientific investigations in history. In the early 17th century, the Italian scientist Galileo Galilei began studying motion through careful experimentation. Galileo had an unusual advantage compared with earlier thinkers. He was not only a philosopher, but also an experimentalist, who believed that questions about nature should be answered through direct observation and measurement. Studying falling objects presented a challenge, however. When objects fall freely under gravity, they accelerate quickly. The motion happens so fast that it becomes difficult to measure accurately with the timing tools available in Galileo's era. Galileo solved this problem with a clever trick. Instead of studying objects falling straight downward, he allowed them to roll down inclined planes. An inclined plane is simply a slanted surface. By rolling a ball down a gentle slope, the acceleration caused by gravity becomes slower and easier to observe. Using this setup, Galileo measured how far a rolling ball travelled over equal intervals of time. What he discovered was remarkable. The distance travelled by the ball did not increase steadily. Instead, it increased more rapidly with each passing moment. This revealed that falling motion involves acceleration. Acceleration means that velocity changes over time. An object in free fall does not move at a constant speed. Instead, it speeds up continuously. Galileo found that the distance travelled by a falling object follows a very specific mathematical relationship. The distance increases in proportion to the square of the time. In modern terms, this relationship can be expressed as distance equals 1/2 multiplied by gravitational acceleration multiplied by time squared. This formula describes how far an object falls during a given amount of time under constant gravitational acceleration. Although Galileo did not write the equation exactly in this form, he understood the underlying principle. His experiment showed that nature followed precise mathematical rules. This conclusion directly challenged Aristotelian physics. Aristotle had described motion using philosophical arguments and qualitative reasoning. Galileo replaced that approach with measurement, experiment, and mathematics. The difference between these two approaches cannot be overstated. Under Aristotle's framework, explanations relied on logic and common sense. Under Galileo's approach, explanations had to match measurable evidence. This shift marked the beginning of modern experimental science. Galileo's studies of motion also led him to an important realization about inertia. If friction and air resistance could be completely removed, a moving object would not naturally slow down and stop. Instead, it would continue moving indefinitely at a constant speed. This idea was revolutionary because it overturned the ancient assumption that rest was the natural state of objects. In Galileo's view, uniform motion could be just as natural as rest. The only reason objects appear to slow down in everyday life is because forces such as friction constantly interfere. If those forces vanished, motion would persist. This insight would later become a central principle of physics known as inertia. Although Galileo laid the groundwork, the full formulation of inertia would eventually appear in the work of another scientist whose ideas transformed physics entirely. But the key point is that Galileo did not arrive at his conclusions in isolation. His work built upon centuries of earlier thinking. The medieval ideas of Jean Buridan, the observations of Giambattista Benedetti, and the accumulated challenges to Aristotelian doctrine all contributed to a gradual shift in perspective. Scientific revolutions rarely happen overnight. Instead, they emerge from long chains of questioning, refinement, and incremental progress. Each generation of thinkers examines the ideas they inherit, tests them against observation, and slowly improves them. Over time, the pieces begin to fit together. By the early 17th century, the foundations were finally in place for a completely new understanding of motion, a framework that would soon reveal that the same rules governing falling apples could also describe the motion of planets. But that realization required one more extraordinary leap in thinking, made possible by centuries of patient curiosity and the quiet determination to ask a simple question. How exactly does the universe move? By the middle of the 17th century, a quiet transformation had begun unfolding across Europe. Astronomers were mapping the skies with increasing precision. Mathematicians were developing new tools for describing change and motion. Experimenters were beginning to treat nature as something that could be measured, tested, and understood through careful observation. Into this environment stepped a young English scholar named Isaac Newton. Newton was born in the year 1642 in the small village of Woolsthorpe in England. By the time he reached his 20s, he had already begun thinking deeply about motion, gravity, and the mathematics required to describe them. The world Newton inherited was already rich with new ideas. Johannes Kepler had discovered that planets orbit the Sun along elliptical paths rather than perfect circles. Galileo Galilei had shown that falling objects accelerate in a predictable way. René Descartes had proposed mechanical explanations for many natural phenomena. Yet these discoveries still felt somewhat separate, like pieces of a puzzle that had not yet been assembled into a single picture. Newton's great achievement was to reveal that these pieces were all connected. In the year 1687, Newton published one of the most influential scientific books ever written. Its full title was Philosophiae Naturalis Principia Mathematica, which translates into English as Mathematical Principles of Natural Philosophy. Most people simply call it the Principia. Within its pages, Newton presented a new framework for understanding motion and gravity. He introduced 3 fundamental principles that are now known as Newton's laws of motion. The first law describes inertia, the concept that Galileo had already begun to recognize. Newton stated that an object will remain at rest, or continue moving at a constant speed in a straight line, unless acted upon by an external force. This idea may sound straightforward, but it represented a dramatic shift from earlier thinking. According to this principle, motion does not require continuous pushing. Instead, motion persists naturally unless something interferes. The slowing of a rolling ball on the ground is not caused by the absence of force. It is caused by forces such as friction and air resistance gradually opposing the motion. Newton's second law introduced a precise mathematical relationship between force, mass, and acceleration. In clear language, it can be written as force equals mass multiplied by acceleration. This simple statement carries enormous power. It means that if you know the mass of an object and the forces acting upon it, you can calculate exactly how its motion will change. For example, if you push a shopping cart across a supermarket floor, the acceleration of that cart depends on 2 things: the strength of the push and the mass of the cart itself. A heavier cart requires a larger force to produce the same acceleration. This is something anyone who has tried to push a fully loaded trolley quickly discovers. Newton's third law introduced another elegant idea. Whenever one object exerts a force on another object, the second object exerts an equal and opposite force back. In simple terms, every action has an equal and opposite reaction. If you press your hand against a wall, the wall pushes back against your hand with exactly the same force. When a rocket launches into space, the exhaust gases expelled downward push the rocket upward with equal strength. These 3 laws together form the foundation of classical mechanics. But Newton did not stop there. He also solved one of the greatest mysteries in astronomy. For centuries, observers had wondered why the moon circles the Earth, rather than drifting away into space. Why do planets follow stable orbits around the Sun? Newton realized that the same force responsible for an apple falling from a tree could also govern the motion of celestial bodies. That force is gravity. Newton proposed that every object in the universe attracts every other object with the force that depends on their masses and the distance between them. The relationship can be expressed in words like this: gravitational force equals the gravitational constant multiplied by the mass of the first object, multiplied by the mass of the second object divided by the square of the distance between them. This rule is called the inverse square law of gravitation. It means that if the distance between 2 objects doubles, the gravitational force between them becomes 4 times weaker. If the distance triples, the force becomes 9 times weaker. Despite the weakening with distance, gravity never truly disappears. Its influence stretches across enormous distances throughout the universe. Using this single law, Newton demonstrated that the motion of planets around the Sun follows the same principles as the motion of falling objects on Earth. The Moon is constantly falling toward Earth due to gravity. However, it also moves sideways fast enough that it keeps missing the Earth as it falls. The result is an orbit. In fact, the Moon travels around Earth at an average speed of about 1 kilometer per second, which is roughly 2,200 miles per hour. At that speed, its curved path perfectly balances the pull of gravity. This insight united 2 realms that had previously seemed completely separate. Before Newton, many thinkers believed that the heavens obeyed different rules than the Earth. The sky was thought to operate according to special principles reserved for celestial bodies. Newton showed that this distinction was unnecessary. The same laws apply everywhere. The same gravity that pulls a stone toward the ground also governs the motion of planets, moons, and comets. This realization transformed how people understood the universe. Nature was not divided into separate domains with different rules. Instead, the entire cosmos followed a single coherent system of laws. Once those laws were written down, they allowed scientists to predict motion with astonishing accuracy. For example, using Newton's equations, astronomers could calculate the future positions of planets years or even centuries in advance. Engineers could design bridges, ships, and machines using the same principles. The success of Newtonian mechanics gave rise to a powerful new image of the universe. Many thinkers began describing the cosmos as a kind of enormous clockwork mechanism. In this picture, the universe operates like a vast machine whose components follow precise and predictable rules. Once the positions and motions of all objects are known, the future behavior of the system can be calculated. The French mathematician Pierre-Simon Laplace expressed this idea in a famous thought experiment. Laplace imagined an intelligence that could know the exact position and velocity of every particle in the universe at a single moment. With that information, and the laws of physics discovered by Newton, this intelligence could compute both the past and the future of the entire cosmos. Nothing would be uncertain. Everything would unfold according to the predictable consequences of physical laws. Although modern physics has since revealed that nature contains deeper complexities, this vision of a predictable universe dominated scientific thinking for centuries. Newton's framework proved so successful that it remained the foundation of physics from the late 1700s all the way into the early 20th century. Engineers designing steam engines, astronomers predicting planetary motions, and scientists studying fluid flow all relied on Newton's laws. Even today, Newtonian mechanics remains extremely accurate for most everyday situations. If you calculate the trajectory of a baseball thrown across a field, Newton's equations will describe its motion with excellent precision. If you guide a spacecraft toward the moon, mission planners still use Newton's gravitational formulas to calculate its path. Only when objects move extremely fast, approaching the speed of light, or when gravity becomes extremely intense, such as near a black hole, do Newton's laws require modification. For the vast majority of situations encountered in daily life, they remain beautifully reliable. What Newton accomplished was more than just a set of equations. He demonstrated that the universe operates according to universal laws that can be expressed mathematically, tested experimentally, and applied across enormous distances and scales. A falling apple, a spinning planet, and a distant comet all obey the same principles. That idea reshaped science forever, and for more than 200 years it gave humanity the comforting sense that the universe was understandable, orderly, and quietly predictable. After Isaac Newton revealed that motion could be described through precise mathematical laws, many scientists felt as though they had discovered the machinery of the universe. Objects moved because forces acted on them. If you knew the forces and the masses involved, you could calculate exactly how things would accelerate and where they would travel. For a time, this approach seemed to explain nearly everything. But during the 18th century, another idea quietly emerged that offered a completely different way of thinking about motion. Instead of focusing directly on forces pushing objects around, This new perspective suggested that nature might follow a deeper rule, one that selects certain paths over others. At the center of this idea lies something called the principle of least action. The first person to present this concept in a clear form was the French mathematician and philosopher Pierre-Louis Maupertuis. Maupertuis lived during the early 1700s and was deeply interested in understanding why the laws of physics take the particular form that they do. Maupertuis proposed that when a physical system evolves from one state to another, it does so in a way that minimizes a quantity he called action. Action is a measure that combines energy and time. Without diving into overly heavy mathematics, it can be thought of as a quantity that tracks how energy is used as a system moves through time. The principle of least action states that out of all the possible ways a system could move between 2 points, nature selects the path for which the action is minimized, or more precisely made stationary. In simple language, nature behaves as though it is choosing the most efficient path available. At first glance, this might sound almost philosophical. It can even feel a little mysterious. How could an object possibly know which path is the most efficient before it has even taken the journey? But the power of the idea lies in the mathematics. When physicists write down the equations describing action and calculate which path minimizes it, the results match the same motions predicted by Newton's laws. In other words, the principle of least action produces exactly the same physical predictions as Newtonian mechanics, but through an entirely different conceptual route. This discovery fascinated many mathematicians of the 18th century. One of the most important contributors to this development was Joseph Louis Lagrange. Lagrange was born in the city of Turin in the year 1736, and went on to become one of the most influential mathematicians in history. His work transformed the way physicists approached mechanics. Rather than focusing directly on forces and accelerations, Lagrange developed a formulation of mechanics based on energy. He introduced a quantity called the Lagrangian, which is defined as the difference between kinetic energy and potential energy. In words, it can be expressed as the Lagrangian equals kinetic energy minus potential energy. Using this single quantity, Lagrange showed that the motion of a system can be determined by applying the principle of least action. When the action is minimized, the correct equations of motion naturally appear. This approach offered several advantages. First, it allowed physicists to analyze systems with many moving parts more easily. Complex arrangements of pendulums, rotating objects, and mechanical linkages could be described within a unified mathematical framework. Second, it made it easier to apply physics to systems where forces were difficult to visualize directly. The Lagrangian method works equally well whether the system involves particles, rigid bodies, waves, or even fields that extend across space. Another mathematician who expanded these ideas was the Irish physicist William Rowan Hamilton. Hamilton lived during the early 1800s and developed an alternative but closely related framework known as Hamiltonian mechanics. In Hamilton's formulation, the motion of a system is described in terms of energy and quantities called generalized coordinates and generalized momenta. The Hamiltonian itself represents the total energy of the system. In simple terms, the Hamiltonian equals kinetic energy plus potential energy. Hamilton's formulation proved incredibly powerful, especially when physics later expanded into new domains such as quantum mechanics. What makes these approaches so remarkable is that they reveal a deep underlying elegance in nature. Objects do not simply move because forces push them around. Instead, their motion can be described as the result of an optimization principle. Nature behaves as though it is searching for the path that balances energy and time in the most efficient way possible. This idea appears again and again in different areas of physics. Consider the behavior of light. During the 17th century, the French mathematician Pierre de Fermat proposed a principle describing how light travels through space. According to Fermat's principle, light follows the path that requires the least time to travel between 2 points. This principle explains why light bends when it passes from air into water or glass. Because light travels at different speeds in different materials, the quickest route is not always a straight line. Instead, the path bends in exactly the way needed to minimize travel time. This phenomenon is known as refraction. If you place a straw into a glass of water, the straw appears bent at the surface because the light rays leaving the submerged portion follow a time-minimizing path as they pass from water into air. Once again, nature behaves as though it is solving an optimization problem. Light selects the path that requires the least time. Particles follow paths that minimize action. Mechanical systems evolve along trajectories that satisfy these efficiency principles. The same mathematical idea appears across many areas of physics. In classical mechanics, it determines how objects move. In optics, it explains how light travels. In modern field theory, it governs how fields evolve through space and time. Even quantum mechanics, developed in the early 20th century, relies heavily on action-based formulations. The American physicist Richard Feynman later showed that particles in quantum mechanics can be described as exploring many possible paths simultaneously, with the principle of least action emerging from the combined effects of these possibilities. Although the mathematics behind these ideas can become quite sophisticated, the underlying message remains surprisingly simple. Nature displays a deep preference for efficiency. Systems evolve along paths that balance energy and time in remarkably elegant ways. And this elegance is not confined to a single branch of science. The same principles appear whether we study falling objects, bending light rays, vibrating strings, or the motion of entire galaxies. For physicists, this consistency hints at something profound. The laws governing the universe may not be arbitrary collections of rules. Instead, they may emerge from deeper mathematical structures that favor simplicity, symmetry, and efficiency. In many cases, when physicists search for new theories, they look for formulations that minimize action or satisfy related principles. This strategy has proven astonishingly successful. It suggests that the universe operates according to principles that are not only consistent but also beautifully economical. Nature rarely takes a complicated path when a simpler one will do. And in the quiet language of mathematics, that simplicity reveals itself as one of the most reliable guides to understanding how the universe works. For a long time, the universe appeared to behave like an immense and predictable machine. Newton's laws described how objects move when forces act upon them. If you knew the starting conditions of a system and the forces involved, you could calculate exactly what would happen next. Planets followed stable orbits, projectiles traced elegant curves through the air, and mechanical devices could be analysed with precise mathematical equations. This view of nature suggested a deeply deterministic universe. Every event seemed to follow inevitably from what came before. But during the 19th century, physicists began investigating a different class of phenomena. These were processes involving heat, temperature, and the flow of energy. And these studies revealed something surprising. Nature was not only governed by motion and force, it was also governed by energy. Energy is one of the most fundamental concepts in physics. It represents the capacity of a system to perform work or cause change. Energy can appear in many different forms. It can exist as motion, known as kinetic energy. It can be stored in positions or arrangements, known as potential energy. It can appear as heat, light, electricity, or chemical reactions. Despite these many forms, energy obeys one of the most reliable principles in all of science. The total amount of energy in a closed system remains constant. This principle is known as the law of conservation of energy. The idea did not emerge overnight. It grew gradually through the work of several scientists studying heat and mechanical motion. One of the most important figures in this development was the English physicist James Prescott Joule. During the 1800s, Joule conducted a series of careful experiments designed to measure how mechanical work could produce heat. In one famous experiment, Joule used falling weights connected to paddles inside a container of water. As the weights descended, they turned the paddles, stirring the water and gradually raising its temperature. By measuring the amount of work done by the falling weights and the resulting increase in temperature, Joule showed that mechanical energy could be converted directly into heat. He even calculated a precise numerical relationship between the two. Joule discovered that raising the temperature of 1 pound of water by 1 degree Fahrenheit required approximately 772 foot-pounds of mechanical work. This value became known as the mechanical equivalent of heat. Joule's experiments demonstrated that heat was not a mysterious fluid, as many earlier scientists had believed. Instead, heat represented a form of energy associated with the motion of microscopic particles. Around the same time, the German physician and physicist Hermann von Helmholtz expanded these ideas into a broader principle. In 1847, Helmholtz published a paper titled On the Conservation of Force. In this work, he argued that energy could neither be created nor destroyed. Instead, it could only change from one form to another. Mechanical motion could become heat. Heat could produce motion. Chemical reactions could release energy in the form of light or electricity, but the total amount of energy always remained constant. This insight became one of the central pillars of physics. Once scientists understood that energy was conserved, they began examining how energy moved through different systems. This led to the development of thermodynamics, the study of heat, work, and energy transfer. Thermodynamics introduced several laws describing how energy behaves. The first law is simply the law of energy conservation. The second law, however, revealed something deeper and more subtle. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. Entropy is a concept that can feel mysterious at first. In everyday language, it is often described as a measure of disorder, but in physics, entropy is more precisely understood as a measure of probability. To see what this means, imagine a box containing gas molecules. Each molecule moves rapidly in random directions, bouncing off the walls and colliding with other molecules. In just 1 teaspoon of air, there are roughly 10 to the power of 22 molecules. That is a number so large it contains more particles than there are grains of sand on Earth's beaches. Tracking the motion of every individual molecule would be practically impossible. Instead of trying to follow each particle separately, physicists developed a statistical approach. This approach studies the collective behavior of enormous numbers of particles. The scientist who played a central role in this shift was Ludwig Boltzmann. Boltzmann lived during the late 1800s and devoted much of his work to connecting thermodynamics with the microscopic motion of atoms and molecules. Boltzmann proposed that entropy reflects the number of microscopic arrangements corresponding to a particular macroscopic state. For example, imagine gas molecules confined to one half of a container. If a barrier separating the container is suddenly removed, the gas spreads out to fill the entire volume. The molecules could technically return to their original half of the container, but the number of possible arrangements where the gas spreads out evenly is vastly greater. Because those arrangements are overwhelmingly more probable, the gas naturally tends toward that state. Boltzmann captured this relationship in a famous equation engraved on his tombstone in Vienna. Entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microscopic arrangements. This equation reveals a profound connection between probability and physical behavior. Entropy increases not because disorder is inevitable in a philosophical sense, but because systems naturally move toward the most statistically likely configurations. This statistical understanding of nature marked a significant shift in physics. Earlier theories, like Newtonian mechanics, described systems using precise trajectories and deterministic equations. If you knew the exact position and velocity of every particle, you could in principle predict the future perfectly. But statistical mechanics approached the problem differently. Instead of tracking individual particles, it focused on averages, probabilities, and distributions. Another scientist who greatly expanded this approach was the American physicist Josiah Willard Gibbs. Gibbs worked at Yale University during the late 19th century and developed a mathematical framework that unified statistical mechanics. He introduced the concept of ensembles, which are large collections of possible microscopic states that a system might occupy. Rather than analyzing one specific arrangement of particles, Gibbs considered the probabilities of many possible arrangements. From this statistical viewpoint, the macroscopic properties of matter such as temperature, pressure, and entropy emerge naturally. For example, temperature can be understood as a measure of the average kinetic energy of particles in a system. At room temperature, which is roughly 300 Kelvin, molecules in air move at average speeds of about 500 meters per second. That is more than 1,000 miles per hour. Fortunately for us, those molecules move in random directions and collide constantly with each other, preventing the atmosphere from turning into an invisible hurricane. The statistical approach pioneered by Boltzmann and Gibbs allowed physicists to understand how simple microscopic rules give rise to complex macroscopic behavior. This realization also softened the strictly deterministic picture of the universe. Even if the underlying laws remain precise, the behavior of large systems often becomes best described through probabilities. Weather systems, turbulent fluids, and the motion of countless atoms cannot realistically be predicted in exact detail. Instead, physicists describe their behavior using statistical laws that predict average outcomes and probable patterns. In this sense, physics gradually expanded beyond the clockwork view of the universe. The laws of motion still applied, but they are now accompanied by laws governing energy flow, probability, and large-scale behavior. And through this shift, scientists began to see that the universe operates not only through precise mechanisms, but also through the quiet mathematics of statistics. An enormous collection of tiny, random motions can produce the stable and predictable world we experience every day. A warm cup of tea gradually cools, gas spreads evenly through a room, stars shine steadily for billions of years. All of these processes are guided by the same underlying principles of energy conservation and statistical probability, and together they reveal that the universe is both orderly and subtle. Beneath the calm surface of everyday experience lies a ceaseless dance of countless particles, moving, colliding, exchanging energy, and quietly shaping the physical world around us. For a long time, scientists imagined forces acting directly between objects across empty space. If two objects attracted one another through gravity, the explanation was simple. Each object pulled on the other with a force. The strength of that force depended on their masses and the distance between them. This picture worked extremely well mathematically. Newton's law of gravitation predicted the motion of planets and moons with extraordinary precision. But there was one aspect of the theory that quietly troubled many thinkers. How could one object influence another across empty space without anything connecting them? This puzzle became known as the problem of action at a distance. Imagine the Earth pulling on the Moon through gravity. The two objects are separated by nearly 400,000 kilometers. What exactly carries the force between them? How does the Earth know where the Moon is, and how does the Moon respond instantly? Newton himself admitted that he did not know the mechanism behind gravity. His equations described how the force behaved, but they did not explain how the interaction was transmitted. During the 19th century, a different way of thinking began to emerge. Instead of imagining forces jumping directly between distant objects, scientists began considering the possibility that space itself might contain something more subtle. Perhaps space was not empty at all. Perhaps it contained invisible structures capable of transmitting physical influence. This idea eventually became known as the concept of a field. A field is a physical quantity defined at every point in space. Rather than forces acting instantaneously between objects, each object modifies the surrounding space, creating a field that influences other objects nearby. One of the most important pioneers of this idea was Michael Faraday. Faraday was born in England in the year 1791 and began life with little formal education. As a young man, he worked as a bookbinder's apprentice, reading scientific texts while repairing their covers. Despite his modest beginnings, Faraday possessed extraordinary experimental skill and an exceptional ability to visualize physical processes. During the 1820s and 1830s, Faraday began studying electricity and magnetism. These two phenomena had already been known for centuries. Static electricity could be produced by rubbing certain materials together, while magnets could attract iron and orient compass needles toward the north. But the deeper relationship between electricity and magnetism remained mysterious. Faraday conducted a long series of experiments investigating how electric currents and magnetic fields interact. One of his most important discoveries came in the year 1831, when he demonstrated electromagnetic induction. Faraday found that moving a magnet near a coil of wire could produce an electric current within the wire. Similarly, changing the strength of a magnetic field around a conductor could generate electricity. This discovery revealed that electricity and magnetism were not separate phenomena. They were deeply connected. Electromagnetic induction became the operating principle behind electric generators and transformers, devices that still power modern electrical systems. Faraday's experiments also led him to develop a new way of visualizing physical interactions. Instead of imagining invisible forces reaching instantly across space, Faraday pictured space filled with lines of influence. He called these structures lines of force. If you sprinkle iron filings around a magnet, They arrange themselves into curved patterns that trace the shape of the magnetic field surrounding the magnet. Faraday interpreted these patterns as evidence that the space around the magnet had been altered. The magnet created a magnetic field extending outward in all directions. Objects placed within that field experienced forces not because the magnet reached out to them directly, but because the field at that location exerted an influence. This idea represented a profound shift in perspective. Space was no longer a passive stage where physical events occurred. Instead, space itself could contain physical properties. A magnet created a magnetic field. An electric charge produced an electric field. These fields filled the surrounding space and influenced other objects that entered them. Faraday expressed these ideas primarily through experiments and visual intuition, rather than complex mathematics, but his insights inspired another scientist who possessed both theoretical brilliance and mathematical skill. That scientist was the Scottish physicist James Clerk Maxwell. Maxwell was born in 1831 and became one of the most influential theoretical physicists of the 19th century. Building on Faraday's experimental discoveries, Maxwell set out to describe electricity and magnetism using precise mathematical equations. The result was one of the most elegant theories ever developed in science. Maxwell showed that electric and magnetic fields are interconnected and can influence each other dynamically. A changing electric field can produce a magnetic field. A changing magnetic field can produce an electric field. When these two processes interact continuously, they produce self-sustaining waves that travel through space. Maxwell calculated the speed of these waves and found something astonishing. Their predicted speed was about 300,000 kilometers per second. This value matched the measured speed of light almost exactly. From this result, Maxwell concluded that light itself is an electromagnetic wave. In other words, visible light, radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays are all different forms of the same underlying phenomenon. They are oscillations of electric and magnetic fields moving through space. Maxwell's theory unified electricity, magnetism, and light into a single framework, now known as electromagnetism. His equations describe how electric charges generate fields, how those fields evolve over time, and how electromagnetic waves propagate. These equations can be written in several mathematical forms, but their meaning can be summarized in words. Electric charges produce electric fields. Moving charges produce magnetic fields. Changing magnetic fields create electric fields. Changing electric fields create magnetic fields. Together, these relationships describe the dynamic behavior of electromagnetic fields throughout space. Maxwell originally expressed his theory using a rather complicated system of equations involving many components. Later, a British physicist named Oliver Heaviside simplified the mathematics dramatically. During the late 1800s, Heaviside reformulated Maxwell's theory using vector notation, a mathematical language that represents quantities with both magnitude and direction. This new formulation condensed Maxwell's original work into 4 compact equations that are now taught in physics courses around the world. Heaviside's mathematical restructuring made the theory far easier to apply and helped establish electromagnetism as one of the central pillars of modern physics. The idea of fields soon extended beyond electricity and magnetism. Physicists began realizing that gravity itself could also be described as a field. Instead of objects pulling directly on one another, each mass creates a gravitational field in the surrounding space. Other masses respond to the field present at their location. Later developments in physics expanded this concept even further. Quantum field theory now describes every fundamental particle as an excitation in an underlying field. Electrons arise from the electron field. Photons arise from the electromagnetic field. In this picture, fields are not just mathematical tools. They are the fundamental building blocks of reality. Every point in space contains these fields, constantly fluctuating and interacting. Particles appear as localized disturbances moving through them, much like ripples traveling across the surface of water. The universe, in this view, is filled with invisible structures that shape how matter and energy behave. Even in regions that appear empty, fields are present. They quietly carry forces, transmit waves, and connect distant parts of the cosmos through subtle interactions. What began as an attempt to understand magnets and electric currents ultimately revealed something much deeper. Space itself possesses structure, and within that structure, invisible fields form the framework through which much of the universe operates. For most of human history, matter appeared continuous. A stone could be broken into smaller pieces, and those pieces could be broken again. Powder could be ground ever finer. Water could be divided into droplets and droplets into mist. To the naked eye, there seemed to be no clear limit to how far this process could go. Yet many thinkers suspected that this endless divisibility might eventually stop. Perhaps matter was built from tiny units so small that they could not be split any further. More than 2,000 years ago, the Greek philosopher Democritus suggested that everything might be made from indivisible particles he called atoms, from the Greek word meaning uncuttable. But for centuries this idea remained philosophical speculation rather than experimental science. It was not until the early 19th century that atomic theory began to take on a scientific form. One of the key figures in this development was the English chemist John Dalton. Dalton worked during the early 1800s and was deeply interested in understanding how chemical substances combine with one another. Through careful experiments, chemists had already noticed something intriguing. When elements react to form compounds, they combine in fixed ratios by mass. For example, water always forms when hydrogen and oxygen combine in a specific proportion. Approximately 2 grams of hydrogen react with about 16 grams of oxygen to produce 18 grams of water. These ratios remain consistent no matter where the reaction takes place. Dalton realized that such regular patterns made sense if matter consisted of discrete particles. In his atomic theory, each chemical element was composed of atoms with characteristic masses. When elements combine, their atoms join together in simple numerical ratios. Water, for instance, contains 2 hydrogen atoms for every oxygen atom. Dalton's model was simple but powerful. It provided a framework that explained why chemical reactions follow predictable rules. Although Dalton could not see atoms directly, his theory suggested that the microscopic structure of matter was responsible for the observable patterns in chemistry. As chemists continued studying different elements, they began noticing additional regularities. One of the most remarkable insights came from the Russian chemist Dmitry Mendeleev. In the year 1869, Mendeleev arranged known chemical elements according to their atomic masses and chemical properties. When he organized them into rows and columns, a striking pattern emerged. Elements with similar chemical behaviors appeared at regular intervals. This arrangement became known as the periodic table. Mendeleev's table revealed that the properties of elements repeat periodically as atomic mass increases. For example, elements such as lithium, sodium, and potassium share similar chemical characteristics. Each reacts vigorously with water and forms compounds with comparable structures. These similarities arise because their atoms possess comparable internal arrangements. What made Mendeleev's work especially impressive was his willingness to leave gaps in the table. Where patterns suggested the existence of unknown elements, he predicted their properties in advance. In several cases, those elements were discovered later with characteristics closely matching his predictions. The periodic table did more than organize chemical knowledge. It provided strong evidence that matter follows deep structural rules. Atoms were not random collections of substance. They possessed internal structures that determined how they interacted with other atoms. Yet even as atomic theory gained acceptance, scientists still did not know what atoms themselves were made of. Many people imagined atoms as solid, indivisible spheres. That picture began to change toward the end of the 19th century with the discovery of radioactivity. In 1896, the French physicist Henri Becquerel was studying minerals containing uranium. While investigating whether these materials emitted light after exposure to sunlight, he made an unexpected observation. Even when stored in darkness, uranium salts produced mysterious rays capable of exposing photographic plates. These rays appeared to originate from within the atoms themselves. Soon afterward, the Polish-born physicist Marie Curie and her husband Pierre Curie began investigating this phenomenon in greater detail. Working in Paris, the Curies discovered that certain elements emitted powerful radiation spontaneously, without any external stimulus. Marie Curie coined the term radioactivity to describe this process. Her research led to the discovery of two new radioactive elements, polonium and radium. These materials released enormous amounts of energy as their atoms transformed into different elements over time. Radioactivity revealed something astonishing. Atoms were not immutable building blocks after all. They could change, break apart, and release energy in the process. Inside each atom lay an intricate internal structure. As scientists investigated radioactive decay, they discovered that atoms contain smaller components, electrons, which carry negative electric charge, occupy regions surrounding the atom's center. At the center lies the nucleus, an extremely dense core composed of protons and neutrons. The nucleus is incredibly small compared with the overall size of the atom. If an atom were expanded to the size of a large sports stadium, the nucleus would occupy a region only about the size of a small marble placed at the center. Despite its tiny size, the nucleus contains nearly all the mass of the atom. Radioactive processes occur when unstable nuclei rearrange themselves, emitting particles and radiation as they transform into more stable forms. These discoveries opened the door to nuclear physics. Among the scientists who helped explain nuclear processes was the Austrian-Swedish physicist Lise Meitner. During the 1930s, Meitner collaborated with the chemist Otto Hahn in studying how uranium atoms behave when bombarded with neutrons. In the year 1938, Hahn and his colleague Fritz Strassmann observed that neutron bombardment caused uranium nuclei to split into smaller elements such as barium. At first, the result seemed puzzling. How could such a heavy atom break into two much lighter pieces? Lise Meitner provided the crucial explanation. She realized that the uranium nucleus was undergoing a process now known as nuclear fission. When a uranium nucleus absorbs a neutron, it can become unstable and split into two smaller nuclei. This splitting releases additional neutrons and an enormous amount of energy. The energy released during nuclear fission comes from a small loss of mass. According to the principle expressed in Albert Einstein's famous equation, energy equals mass multiplied by the speed of light squared, even a tiny amount of mass can produce a tremendous amount of energy because the speed of light is extraordinarily large. The speed of light in empty space is approximately 300,000 kilometers per second. When this value is squared, the resulting number is enormous. As a result, converting just 1 gram of mass entirely into energy would release roughly the same energy as several tens of thousands of tons of chemical explosives. Fortunately, most nuclear reactions convert only a small fraction of mass into energy. Even so, the energy released during fission can be immense. These discoveries revealed that atoms are far from simple. Instead of being indivisible spheres, atoms contain complex internal structures involving charged particles, nuclear forces, and energy transformations. Matter itself turned out to possess layers of organization. Atoms consist of nuclei and electrons. Nuclei contain protons and neutrons, and those particles, as later research would reveal, are themselves composed of even smaller constituents. The exploration of radioactivity and nuclear structure opened a new window into the physical world. What once seemed like solid, unchanging matter turned out to be a dynamic system of interacting particles and energy. And the deeper scientists looked, the more intricate the structure of matter became. By the end of the 19th century, many scientists believed that physics was nearly complete. Newton's laws explained motion. Maxwell's equations described electricity, magnetism, and light. Thermodynamics governed heat and energy. Together, these theories appeared to form a coherent and reliable picture of the physical world. There were still puzzles, of course, but many physicists believed those remaining problems would soon be solved with small adjustments to existing theories. Instead, those puzzles opened the door to one of the most dramatic revolutions in scientific history. The trouble began with an apparently simple question. What happens when objects become extremely small? At the scale of atoms and subatomic particles, classical physics began producing predictions that did not match experimental results. One of the earliest signs of this trouble appeared in the study of something called blackbody radiation. A blackbody is an idealized object that absorbs all incoming radiation and then re-emits energy in the form of electromagnetic waves. Heated objects, such as glowing metal or the surface of a star, behave approximately like blackbodies. Scientists studying heated materials noticed that they emitted light with specific patterns of intensity, depending on the wavelength. When physicists tried to calculate this pattern using classical physics, they encountered a serious problem. According to classical predictions, the amount of radiation emitted at shorter wavelengths should increase without limit. As wavelength became smaller and smaller, the predicted energy output would rise toward infinity. This absurd prediction became known as the ultraviolet catastrophe. Clearly, something in the theory was wrong. In the year 1900, the German physicist Max Planck proposed a radical solution. Planck suggested that energy is not emitted continuously, as classical physics assumed. Instead, energy is released in discrete packets. He called these packets quanta. According to Planck's idea, electromagnetic radiation could only be emitted or absorbed in specific amounts determined by the frequency of the radiation. This relationship can be expressed in words as energy equals Planck's constant multiplied by frequency. Planck's constant is an extremely small number that sets the scale at which quantum effects become important. Although Planck initially viewed his idea as a mathematical trick rather than a physical reality, it solved the black-body radiation problem perfectly. Soon, other scientists began realizing that the quantum idea had deeper implications. One of those scientists was Albert Einstein. In 1905, Einstein used Planck's concept of energy quanta to explain the photoelectric effect. In this phenomenon, light shining on a metal surface can eject electrons from the material. Classical wave theory predicted that increasing the brightness of light should increase the energy of the emitted electrons. But experiments showed something different. Only light above a certain frequency could eject electrons at all. Einstein explained this by proposing that light itself behaves as if it consists of individual particles called photons. Each photon carries a discrete amount of energy determined by its frequency. This was a surprising conclusion. Light had long been understood as a wave. Now it appeared to possess particle-like properties as well. As scientists explored atomic structure further, more strange behaviors appeared. In the year 1913, the Danish physicist Niels Bohr proposed a model of the atom that incorporated quantum ideas. Bohr suggested that electrons orbit the atomic nucleus in specific allowed paths called energy levels. Electrons cannot exist between these levels. They can only occupy certain discrete orbits. When an electron jumps from a higher energy level to a lower one, it emits a photon of light. The energy of that photon corresponds exactly to the difference between the two levels. Bohr's model successfully explained the spectral lines produced by hydrogen atoms, which had puzzled scientists for decades. Although later developments would refine and replace Bohr's picture, his model marked an important step toward understanding atomic behavior. As the 1920s approached, physicists realized that a deeper theoretical framework was needed. Two scientists played central roles in developing that framework. One was the German physicist Werner Heisenberg. The other was the Austrian physicist Erwin Schrödinger. Heisenberg introduced a mathematical approach known as matrix mechanics. Instead of describing precise trajectories for particles, Heisenberg focused on observable quantities such as energy levels and transition probabilities. During this work, Heisenberg discovered a profound principle. It is impossible to measure certain pairs of physical properties simultaneously with unlimited precision. The most famous example involves position and momentum. The more precisely a particle's position is known, the less precisely its momentum can be determined. This relationship is expressed in the uncertainty principle. In words, the idea can be summarized as the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a small constant related to Planck's constant. The uncertainty principle is not simply a limitation of measurement technology. It reflects a fundamental property of nature. At very small scales, particles do not possess perfectly defined positions and momenta simultaneously. Instead, their behavior must be described in terms of probabilities. Around the same time, Erwin Schrödinger developed another formulation of quantum theory. Schrödinger proposed that particles could be described by wave-like mathematical functions. These functions, called wave functions, contain information about the probability of finding a particle in different locations. The equation governing the evolution of these wave functions is now known as the Schrödinger equation. In words, it states that the change of a particle's wave function over time depends on its energy and the forces acting upon it. Solving the Schrödinger equation allows physicists to calculate the probability distributions associated with particles. Instead of predicting a single definite outcome, quantum mechanics predicts a range of possible outcomes with specific probabilities. Another important contribution came from the Indian physicist Satyendra Nath Bose. In the year 1924, Bose developed a new statistical method for describing the behavior of particles that do not obey the usual rules of classical statistics. Bose sent his work to Albert Einstein, who immediately recognized its importance and helped publish it. The statistical framework they developed became known as Bose-Einstein statistics. Particles that follow these statistics are now called bosons. Examples include photons, the particles of light. Bose-Einstein statistics revealed that certain particles can occupy the same quantum state simultaneously. This property leads to remarkable phenomena such as Bose-Einstein condensation, where large numbers of particles behave collectively as a single quantum system. Quantum theory ultimately transformed our understanding of matter and energy. At the microscopic scale, nature does not behave like a predictable clockwork machine. Particles behave partly like waves and partly like particles. Their properties cannot always be defined with perfect certainty. Outcomes must often be described in terms of probabilities, rather than deterministic predictions. Despite its unusual features, quantum mechanics has proven extraordinarily successful. It accurately explains the structure of atoms, the behavior of chemical reactions, the operation of lasers, the properties of semiconductors, and the interactions of fundamental particles. Much of modern technology, including computers, medical imaging devices, and solar panels, relies directly on principles derived from quantum theory. The strange rules governing atoms and subatomic particles have reshaped our understanding of reality. Instead of a universe built entirely on certainty, physics now reveals a world where probability, uncertainty, and wave-like behavior play fundamental roles. And beneath the calm appearance of everyday objects lies a restless quantum landscape, where particles exist as patterns of possibility until observation brings those possibilities into focus. There is a quiet pattern that appears again and again throughout physics, one that is so fundamental that many physicists now see it as one of the deepest organizing principles of the universe. That pattern is symmetry. In everyday language, symmetry refers to balance or similarity under certain transformations. A snowflake, for example, displays six-fold symmetry. If you rotate it by 1/6 of a full circle, it looks the same as before. A perfectly round sphere has even greater symmetry. It looks identical no matter how you rotate it. At first glance, symmetry may seem like a purely aesthetic feature, something pleasing to the eye but not necessarily important for understanding nature. Yet physics has revealed something far more remarkable. The laws governing the universe appear to be deeply connected to symmetry. In fact, many of the most important conservation laws in physics exist precisely because certain symmetries hold true. To see how this works, imagine performing an experiment today and then repeating the same experiment tomorrow. If the laws of physics are the same on both days, then the outcome should not depend on the date on the calendar. This simple idea represents a symmetry of time. The laws of nature do not change simply because time passes. It turns out that this symmetry has a profound consequence. Because the laws of physics remain the same over time, energy must be conserved. Energy cannot appear out of nowhere or vanish without a trace. The total amount of energy in a closed system stays constant. Now consider another type of symmetry. Suppose you conduct an experiment in one location and then repeat the same experiment in another place. The laws of physics should behave the same way whether you're in London, Tokyo, or on a quiet mountaintop somewhere far from city lights. This uniformity represents a symmetry of space. The laws of physics do not depend on where an experiment happens. From this spatial symmetry arises another conservation law. Momentum must be conserved. Momentum describes the quantity of motion possessed by an object. It combines mass and velocity into a single measure of motion. In words, the relationship is expressed as momentum equals mass multiplied by velocity. Because the laws of physics remain the same everywhere in space, the total momentum of an isolated system cannot change. A third symmetry appears when we rotate physical systems. Imagine observing a spinning wheel. If you rotate the entire system by 90 degrees, the underlying physical laws do not suddenly change. The laws of physics remain the same regardless of orientation. This symmetry under rotation leads to the conservation of angular momentum. Angular momentum measures the rotational motion of objects. A familiar example occurs when an ice skater pulls their arms inward while spinning. As the skater's arms move closer to their body, their rotation speeds up. This happens because the total angular momentum must remain constant. These connections between symmetry and conservation laws were revealed through the work of one remarkable mathematician. Her name was Emmy Noether. Emmy Noether was born in Germany in the year 1882 and became one of the most influential mathematicians of the 20th century. At a time when women faced enormous barriers in academic life, Noether produced groundbreaking work in abstract algebra and theoretical physics. In the year 1918, she proved a theorem that transformed how scientists understand the structure of physical laws. Noether's theorem shows that every continuous symmetry of the laws of physics corresponds to a conservation law. If the laws of physics remain unchanged under shifts in time, energy is conserved. If the laws remain unchanged under shifts in position, momentum is conserved. If the laws remain unchanged under rotation, angular momentum is conserved. This relationship revealed that conservation laws are not arbitrary rules imposed on nature. They arise directly from the underlying symmetries of the universe. Noether's theorem provided a deep explanation for why conservation laws exist at all. Instead of being independent principles, they emerge naturally from the symmetrical structure of physical laws. As physics continued to develop during the 20th century, the importance of symmetry grew even more apparent. Scientists began discovering that fundamental interactions between particles could also be understood through more subtle types of symmetry. One of the most important of these is called gauge symmetry. Gauge symmetry describes a kind of mathematical freedom in the way certain physical quantities can be represented. Although the details can become quite technical, the essential idea is surprisingly elegant. Certain transformations can be applied to the mathematical description of a physical system without changing any observable outcomes. When a theory possesses this kind of symmetry, it naturally requires the existence of specific fields that mediate interactions between particles. For example, the electromagnetic force arises from a gauge symmetry associated with electric charge. This symmetry leads to the existence of the photon, the particle responsible for transmitting electromagnetic interactions. Modern particle physics extends this idea even further. The standard model of particle physics describes three fundamental forces using gauge symmetries: the electromagnetic force, the weak nuclear force, and the strong nuclear force, Each emerge from different symmetry structures embedded in the mathematical framework of the theory. These symmetries determine how particles interact, how forces behave, and how energy flows through the microscopic world. In many ways, modern theoretical physics has become a search for deeper and more elegant symmetries. When physicists attempt to develop new theories, they often begin by asking which symmetries the laws of nature should possess. Once the correct symmetries are identified, the mathematical structure of the theory often follows naturally. This approach has guided major discoveries in fields ranging from particle physics to cosmology. It has even inspired attempts to unify all known forces within a single theoretical framework. Symmetry also appears throughout nature beyond fundamental physics. Crystals form repeating geometric patterns because the arrangement of atoms follows symmetrical structures. Snowflakes grow into intricate six-sided shapes due to the symmetry of water molecules. Even large-scale cosmic structures can display surprising degrees of symmetry, such as the roughly spherical shape of stars and planets shaped by gravity. These patterns remind us that symmetry is not just a mathematical curiosity. It is a guiding principle woven deeply into the fabric of reality. And perhaps most remarkably, a concept that begins with something as simple as balance or repetition ultimately leads to profound insights about why the universe obeys the laws that it does. Through symmetry, physicists have discovered that the universe is not only governed by rules. Those rules themselves appear to follow an elegant and interconnected logic. By the early decades of the 20th century, physics had already uncovered something astonishing about nature. Light behaved both like a wave and like a particle. Electrons displayed wave-like properties while still acting as discrete objects in experiments. Atoms emitted energy in sharply defined amounts rather than in smooth continuous flows. Quantum mechanics had successfully explained these strange behaviors, yet a deeper challenge remained. How could the theory of quantum particles be combined with the theory of fields that described electricity and magnetism? Classical electromagnetism, developed by James Clerk Maxwell, treated electric and magnetic fields as continuous entities filling space. Quantum mechanics, on the other hand, described matter as collections of particles governed by probability. Physicists soon realized that these two descriptions needed to be unified. The solution came in the form of a powerful framework now known as quantum field theory. In quantum field theory, the fundamental entities of nature are not particles at all. Instead, the universe is filled with fields that exist everywhere in space. Each type of particle corresponds to its own underlying field. An electron arises from the electron field. A photon arises from the electromagnetic field. Other particles emerge from their own corresponding fields. In this picture, particles are not tiny solid objects traveling through empty space. They are localized excitations, small ripples or vibrations occurring within these fields. An analogy can help make this idea more intuitive. Imagine the surface of a calm lake. The water extends smoothly across the entire surface. If a stone is dropped into the lake, ripples spread outward from the point of impact. Those ripples are not separate objects existing independently from the water. They are patterns of motion within the water itself. Quantum field theory describes particles in a similar way. A particle is like a ripple traveling through a field. The field exists everywhere, and the particle represents a localized disturbance moving within it. One of the first major breakthroughs leading toward this understanding came from the British physicist Paul Dirac. In the late 1920s, Dirac was attempting to combine quantum mechanics with Einstein's theory of special relativity. Special relativity had shown that space and time are interconnected, and that the speed of light represents a fundamental limit for motion and information. Any complete theory of particles needed to respect these principles. Dirac developed a new mathematical equation describing the behavior of electrons moving at relativistic speeds. The equation successfully predicted several known properties of the electron, including its intrinsic angular momentum known as spin. But Dirac noticed something unexpected in the solutions to his equation. Alongside the familiar positive energy states corresponding to ordinary electrons, the equation also produced solutions with negative energy. At first, this seemed like a mathematical oddity. However, Dirac realized that these negative energy states might correspond to a new type of particle. In the year 1931, he proposed the existence of particles identical to electrons in mass, but carrying the opposite electric charge. These hypothetical particles became known as positrons. A few years later, in 1932, the American physicist Carl Anderson observed exactly such particles in cosmic ray experiments conducted at the California Institute of Technology. The positron became the first confirmed example of antimatter. Antimatter consists of particles that mirror ordinary matter but possess opposite charges. An electron carries negative charge. A positron carries positive charge. When matter and antimatter meet, they can annihilate one another, converting their mass into energy according to Einstein's famous relationship. Energy equals mass multiplied by the speed of light. Square Dirac's equation revealed that quantum theory naturally predicts the existence of antimatter. This was one of the first signs that the mathematical structures underlying physics might reveal entirely new aspects of reality. As the theory continued developing, physicists faced another challenge. When they tried calculating interactions between electrons and photons using early quantum theories, the results often produced infinities. For example, certain calculations predicted infinite energies or infinite probabilities, which clearly made no physical sense. Solving this problem required new mathematical techniques. Several physicists made crucial contributions to this effort during the 1940s. Among them were Julian Schwinger in the United States, Shinichiro Tomonaga in Japan, and Richard Feynman at Cornell University. Working independently, these scientists developed methods that allowed quantum electrodynamics to produce finite, accurate predictions. Quantum electrodynamics, often abbreviated as QED, describes how electrons interact with photons through the electromagnetic field. The theory explains how charged particles emit and absorb light, how electromagnetic forces operate at the quantum level, and how particles exchange energy through photon interactions. One of the remarkable achievements of quantum electrodynamics is its extraordinary accuracy. When physicists calculate certain properties of the electron using QED, the predictions match experimental measurements to more than 10 decimal places. In everyday terms, that level of agreement would be like predicting the distance from Earth to the Moon. With an error smaller than the width of a human hair, Richard Feynman played a particularly important role in making the theory easier to visualize. He introduced graphical tools now known as Feynman diagrams. These diagrams represent particle interactions as simple line drawings. Lines represent particles such as electrons or photons, while points where lines meet represent interactions. Although the diagrams may appear simple, they encode complex mathematical calculations describing how particles exchange energy and momentum. Another physicist who helped clarify the structure of these ideas was Freeman Dyson. Dyson demonstrated that the different mathematical approaches developed by Schwinger, Tomonaga, and Feynman were actually equivalent descriptions of the same underlying theory. His work unified these methods and established quantum electrodynamics as a consistent and powerful framework. Through these developments, physicists gradually realized that the language of fields offered the most natural description of the microscopic world. Particles are not fundamental objects moving through empty space. Instead, fields are fundamental. Every particle corresponds to a quantum of vibration in its respective field. The electron field fills the entire universe. Whenever that field vibrates in a particular way, an electron appears. The electromagnetic field also permeates all space. When that field oscillates, a photon emerges. Modern particle physics extends this idea further. Protons and neutrons arise from fields associated with quarks and gluons. Neutrinos correspond to their own fields. Even the recently discovered Higgs boson originates from the Higgs field, a field believed to exist throughout the universe. This view transforms our understanding of matter. What once appeared to be solid, indivisible particles are now understood as dynamic patterns within underlying fields. Even empty space is not truly empty. It contains fields that are constantly fluctuating at extremely small scales, producing temporary particle pairs that briefly appear and vanish. The universe, in this picture, resembles a vast ocean of interacting fields. Particles are simply the waves travelling through that ocean. And the more physicists explore this framework, the clearer it becomes that the structure of reality may be far more fluid, dynamic, and interconnected than the solid world of everyday experience might suggest. By the middle of the 20th century, physicists had begun uncovering an astonishing variety of subatomic particles. At first, scientists believed that the fundamental components of matter were relatively simple. Atoms contained electrons orbiting a nucleus composed of protons and neutrons. For a time, this picture seemed complete, but as particle accelerators became more powerful during the 1950s and 1960s, experiments began revealing a surprising abundance of new particles. Protons and neutrons themselves could be smashed together at high energies, producing a cascade of unfamiliar fragments. Detectors recorded dozens of previously unknown particles with names such as kaons, pions, and lambdas. The growing collection of subatomic particles became so large that physicists jokingly referred to the situation as the particle zoo. The challenge was clear. If all these particles existed, what deeper structure produced them? Were they all fundamental, or were they built from something even smaller? One of the scientists who brought order to this growing chaos was the American physicist Murray Gell-Mann. In the early 1960s, Gell-Mann proposed that many strongly interacting particles were not elementary at all. Instead, they were combinations of more fundamental constituents. He called these constituents quarks. The name quark came from a playful line in the novel Finnegan's Wake by the Irish writer James Joyce. In the book appears the phrase 3 quarks for muster mark, which Gell-Mann found appealing. According to the quark model, particles such as protons and neutrons are composed of smaller building blocks held together by powerful forces. A proton contains 3 quarks. Specifically, it contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. Each quark carries a fractional electric charge. An up quark has a charge equal to 2/3 of the charge of an electron, while a down quark carries a charge equal to -1/3 of that value. When the charges of three quarks combine within a proton or neutron, the result produces the familiar whole number charges observed in experiments. Quarks are held together by an interaction known as the strong nuclear force. This force is transmitted by particles called gluons, which bind quarks together with extraordinary strength. In fact, the strong force becomes stronger as quarks attempt to move farther apart. This unusual behavior ensures that quarks remain confined within larger composite particles such as protons and neutrons. Although individual quarks cannot normally be isolated, high-energy experiments provide overwhelming evidence for their existence. Over time, physicists discovered that quarks come in several varieties known as flavors. These include up, down, strange, charm, bottom, and top quarks. The names may sound whimsical, but each flavor represents a distinct type of particle with unique mass and properties. While the quark model explained the structure of many particles, physicists were also working to understand the forces governing their interactions. One of the most important advances came from the effort to unify two apparently different forces. The electromagnetic force, responsible for electricity, magnetism, and light, had already been described by Maxwell's equations. Another interaction, known as the weak nuclear force, governs certain types of radioactive decay and nuclear transformations. For many years, these forces appeared unrelated. However, during the 1960s, several physicists realized that they might represent different aspects of a deeper unified interaction. Three scientists played crucial roles in developing this theory. They were Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their work led to what is now called the electroweak theory. According to electroweak theory, the electromagnetic force and the weak nuclear force are actually two manifestations of a single unified interaction. At extremely high energies, such as those that existed in the early universe shortly after the Big Bang, these forces become indistinguishable. As the universe cooled, the unified interaction separated into the distinct electromagnetic and weak forces observed today. Electroweak theory predicted the existence of several previously unknown particles. Among them were the W boson and the Z boson, massive particles responsible for transmitting the weak nuclear force. These particles were eventually observed experimentally in 1983 at the European Organization for Nuclear Research, commonly known as CERN. Their discovery provided powerful confirmation of the electroweak theory and earned the Nobel Prize for several of the scientists involved. But the theory raised another important question. If the electromagnetic and weak forces arise from a unified interaction, why do the particles that carry these forces behave so differently? Photons, the carriers of electromagnetic interactions, have no mass and travel at the speed of light. The W and Z bosons, by contrast, are extremely massive. Each has a mass roughly 80 to 90 times greater than that of a proton. What mechanism gives these particles their mass? This question led to one of the most important theoretical ideas in modern physics. During the 1960s, several physicists, including Peter Higgs, François Englert, and Robert Brute, proposed a solution known as the Higgs mechanism. According to this idea, the universe contains an additional field called the Higgs field. Unlike many other fields that fluctuate dynamically, the Higgs field possesses a constant value throughout space. Particles moving through this field interact with it to varying degrees. Some particles interact strongly with the Higgs field and therefore behave as if they possess large masses. Other particles interact weakly and remain relatively light. Photons do not interact with the Higgs field at all, which is why they remain massless. An analogy can help illustrate the idea. Imagine a large room filled with people. If an unfamiliar person walks through the room, they might pass by easily without attracting much attention. But if a famous celebrity enters, people gather around them, slowing their movement as they travel through the crowd. In this analogy, the crowd represents the Higgs field. Particles that interact strongly with the field experience greater resistance and appear heavier. Particles that interact weakly move more freely and appear lighter. The Higgs mechanism predicted the existence of a new particle associated with the Higgs field itself. This particle became known as the Higgs boson. For decades, physicists searched for evidence of the Higgs boson using increasingly powerful particle accelerators. The breakthrough finally came in the year 2012. At CERN near Geneva, scientists operating the Large Hadron Collider observed signals consistent with the Higgs boson. The Large Hadron Collider is the most powerful particle accelerator ever built. It consists of a circular tunnel roughly 27 kilometers in circumference. Inside this enormous ring, protons are accelerated to energies of several trillion electron volts and then collided at extremely high speeds. These collisions recreate conditions similar to those that existed fractions of a second after the Big Bang. By analyzing the particles produced in these collisions, researchers can probe the fundamental structure of matter. The detection of the Higgs boson confirmed a crucial piece of the theoretical framework known as the Standard Model of particle physics. The Standard Model describes the fundamental particles that make up matter and the forces that govern their interactions. According to this model, all known matter is built from two main classes of particles. The first class consists of quarks. The second class consists of leptons, which include electrons and neutrinos. These particles interact through forces carried by specialized particles known as bosons. Photons carry the electromagnetic force. W and Z bosons carry the weak nuclear force. Gluons transmit the strong nuclear force between quarks. And the Higgs boson arises from the Higgs field responsible for giving particles their mass. Together, these components form one of the most successful scientific theories ever constructed. The Standard Model has been tested in countless experiments and continues to produce predictions that match observations with remarkable precision. Yet even this powerful framework remains incomplete. It does not fully incorporate gravity, nor does it explain several mysteries such as dark matter and dark energy. Nevertheless, the Standard Model represents a remarkable achievement. It reveals that beneath the familiar world of atoms and molecules lies a complex architecture of fields, particles and interactions that govern the structure of matter itself. And with each new experiment, scientists continue probing deeper into that hidden architecture, searching for the next layer of understanding. For centuries, gravity seemed straightforward. Objects fall toward the Earth. The Moon circles our planet. Planets orbit the Sun along predictable paths. Newton's law of gravitation described these motions with remarkable accuracy, and for more than 200 years it served as the foundation for understanding celestial mechanics. Yet there remained a quiet mystery hidden inside Newton's theory. According to Newton's equations, gravity acts instantly across space. If the Sun were somehow moved, Earth would feel the change immediately, regardless of the enormous distance between them. As scientific understanding advanced, this idea began to feel increasingly uncomfortable. The theory of electromagnetism developed by James Clerk Maxwell had already shown that electromagnetic signals travel at a finite speed, specifically the speed of light. This raised a natural question. If light and electromagnetic forces require time to travel through space, should gravity behave the same way? The answer arrived through the work of Albert Einstein. In the year 1915, Einstein presented a new theory of gravity known as general relativity. Rather than describing gravity as a force acting between objects, Einstein proposed something far more radical. Gravity arises from the geometry of space-time itself. To understand this idea, it helps to begin with the simple observation. Space and time are not separate entities. According to Einstein's earlier theory of special relativity, published in 1905, space and time form a unified four-dimensional structure called space-time. Events in the universe are located not only by position in space, but also by their location in time. General relativity extends this idea further by showing that space-time is not rigid or fixed. Instead, space-time can bend and curve in response to mass and energy. The presence of matter alters the geometry of space-time around it. Objects moving through that curved geometry follow paths determined by the shape of space-time itself. In this framework, gravity is no longer a force pulling objects together. Instead, objects move along the natural curves created by the warping of space-time. An analogy often used to visualize this idea involves a stretched rubber sheet. Imagine placing a heavy ball in the center of the sheet. The weight of the ball causes the surface to dip downward. If a smaller ball rolls nearby, it will follow curved paths around the depression. Although the analogy has limitations, it captures the essence of the idea. Massive objects such as planets and stars distort the geometry of space-time around them. Other objects then move along the curved paths defined by that geometry. The mathematical foundation for describing curved spaces was developed decades earlier by the German mathematician Bernhard Riemann. In the year 1854, Riemann introduced a new branch of mathematics known as Riemannian geometry. His work explored how geometry behaves when space itself is curved rather than flat. Although Riemann could not have known it at the time, his ideas provided the precise mathematical language Einstein would later use to describe gravity. Within general relativity, the curvature of space-time is determined by the distribution of mass and energy. The relationship between geometry and energy can be summarized through Einstein's field equations. Expressed in words, these equations state that the curvature of space-time equals a constant multiplied by the distribution of energy and momentum within that space-time. In other words, matter tells space-time how to curve, and curved space-time tells matter how to move. This elegant relationship transformed our understanding of gravity. The theory explained subtle features of planetary motion that Newton's equations could not fully account for. One example involves the orbit of Mercury. Astronomers had noticed that Mercury's orbit slowly shifts over time, a phenomenon called orbital precession. Newtonian gravity predicted most of this effect, but left a small unexplained discrepancy. General relativity accounted for the missing portion perfectly. Einstein's theory also predicted phenomena that had never been observed before. One of these predictions involved the bending of light by gravity. If space-time curves around massive objects, then even light travelling near those objects should follow curved paths. This effect was confirmed in 1919 during a solar eclipse expedition led by Arthur Eddington. When starlight passed close to the Sun, its apparent position shifted slightly due to the curvature of space-time around the Sun. The observation matched Einstein's predictions and quickly brought worldwide attention to his theory. General relativity also revealed that extremely massive objects can produce dramatic distortions of space-time. When stars much larger than the Sun exhaust their nuclear fuel, they may collapse under their own gravity. The Indian-American astrophysicist Subrahmanyan Chandrasekhar studied this process during the 1930s. Chandrasekhar discovered that white dwarf stars, which are dense remnants of collapsed stars, cannot exceed a certain mass limit. If a white dwarf's mass becomes greater than about 1.4 times the mass of the Sun, gravitational forces overwhelm the internal pressure supporting the star. This limit is now known as the Chandrasekhar limit. Beyond this threshold, the star must continue collapsing. Such collapses can produce neutron stars or, if the mass is large enough, black holes. Black holes represent regions where space-time becomes so strongly curved that nothing can escape once it crosses a boundary known as the event horizon. Not even light can escape from within this region. Although black holes were once considered purely theoretical objects, modern astronomy has provided strong evidence for their existence. Observations of stars orbiting invisible massive objects at the centers of galaxies suggest the presence of supermassive black holes containing millions or even billions of times the mass of the Sun. General relativity also predicted another remarkable phenomenon. When massive objects accelerate, they should create ripples in the fabric of space-time itself. These ripples are known as gravitational waves. Gravitational waves travel outward from their source at the speed of light, carrying energy through space-time. For decades, detecting these waves seemed nearly impossible, because the distortions they produce are incredibly small. When a gravitational wave passes through Earth, it changes distances by amounts smaller than the diameter of a proton. Yet scientists eventually developed instruments sensitive enough to measure these tiny effects. In the year 2015, researchers working with the Laser Interferometer Gravitational Wave Observatory, known as LIGO, announced the first direct detection of gravitational waves. The signal came from two black holes spiraling toward each other and merging more than 1 billion light-years away. As the black holes collided, they released enormous amounts of energy in the form of gravitational waves. For a brief moment, the power emitted during that collision exceeded the combined luminosity of all the stars in the observable universe. By the time the waves reached Earth, however, the distortions were incredibly faint. LIGO detected them by measuring minute changes in the lengths of laser beams traveling through long vacuum tunnels several kilometers in length. This discovery confirmed one of the most dramatic predictions of Einstein's theory. It also opened a new field of astronomy. Gravitational wave detectors now allow scientists to observe cosmic events that were previously invisible, including black hole mergers and collisions between neutron stars. Through these observations, researchers can study the behavior of space-time itself under extreme conditions. General relativity reveals that gravity is not simply a force pulling objects together. It is the manifestation of curved space-time. Mass and energy shape the geometry of the universe, and that geometry determines how objects move. From the gentle orbit of the Moon around Earth to the violent collisions of black holes billions of light-years away, this structure of space-time guides the motion of the cosmos. And through the language of geometry, Einstein's theory continues to illuminate the hidden architecture of the universe. As physics progressed through the 20th century, scientists began to notice that many of the deepest questions about nature were not only about matter, energy, or forces. They were also about information. Information might seem like a concept belonging mainly to communication, computers, or libraries full of books. But when physicists began examining how systems store, transmit, and transform information, they discovered that it plays a surprisingly fundamental role in the behavior of the universe. The first clear mathematical framework for understanding information came from the American mathematician Claude Shannon. In the year 1948, Shannon published a groundbreaking paper titled A Mathematical Theory of Communication. His goal was to understand how messages could be transmitted efficiently through noisy communication channels such as telephone lines or radio signals. Shannon introduced a way of measuring information using probabilities. If a message can take many possible forms, the amount of information contained in a specific message depends on how surprising that message is. A message that is highly predictable carries little information. A message that is unexpected carries more. Shannon defined the quantity known as information entropy to measure this uncertainty. The formula he introduced can be expressed in words as information entropy equals the negative sum of each probability multiplied by the logarithm of that probability. Although the mathematics may sound abstract, the idea captures something intuitive. If a coin is perfectly balanced, the result of a flip is uncertain. That uncertainty carries information when the outcome becomes known. But if the coin always lands heads, observing the result provides no new information. Shannon's work transformed communication engineering, enabling the development of modern digital technology. Yet physicists soon realized that Shannon's concept of information entropy closely resembled the entropy already used in thermodynamics. Both quantities measure uncertainty and the number of possible configurations within a system. This connection raised an intriguing possibility. Perhaps information and physical processes are deeply linked. One scientist who explored this idea in detail was the German-American physicist Rolf Landauer. During the 1960s, Landauer studied how information behaves in physical systems such as computers and memory devices. He reached an important conclusion that became known as Landauer's principle. Landauer showed that erasing information is not merely a logical operation, it is also a physical process that requires energy. Specifically, when one bit of information is erased, the system must release a minimum amount of heat into its surroundings. This relationship can be expressed in words as the minimum energy required to erase one bit of information equals Boltzmann's constant multiplied by temperature multiplied by the natural logarithm of 2. Although the amount of energy involved is extremely small for a single bit, the principle carries profound implications. It means that information cannot be separated from the physical world. Information is not an abstract concept floating above reality. It is tied directly to energy, temperature, and the laws of thermodynamics. The act of storing, copying, or deleting information always involves physical processes. Another physicist who pushed this idea even further was John Archibald Wheeler. Wheeler had worked with both Niels Bohr and Albert Einstein, and he spent much of his career exploring the philosophical implications of modern physics. In the 1980s, Wheeler proposed a provocative phrase to summarize his thinking. He called it from bit. By this he meant that every physical object, every particle, every field, and even space-time itself might ultimately arise from fundamental units of information. According to Wheeler's view, the basic building blocks of the universe may not be matter or energy alone. Instead, they might be answers to yes or no questions. Each measurement, each interaction, each observation could represent a binary choice between alternatives. Out of countless such informational decisions, the structure of reality emerges. While Wheeler's proposal remains speculative, it has inspired many researchers working in areas such as quantum information theory and quantum computing. These fields investigate how information behaves when encoded in quantum systems. Quantum bits, or qubits, can exist in combinations of states that allow entirely new forms of computation. In recent years, physicists have even begun exploring whether the geometry of spacetime itself might be connected to patterns of quantum information. The idea that information lies at the heart of physics naturally leads to another fascinating question. How do complex structures arise in a universe governed by relatively simple laws? For example, the laws of physics that describe atoms and molecules are comparatively straightforward. Yet from those laws emerge oceans, weather systems, living organisms, ecosystems, and entire civilizations. This transformation from simple rules to complex behavior is studied within a field known as complex system science. One of the pioneers in this area was the Belgian chemist and physicist Ilya Prigogine. Prigogine studied systems that operate far from equilibrium, meaning systems where energy and matter flow continuously through them. Examples include chemical reactions, atmospheric circulation, and biological processes. Prigogine discovered that under certain conditions, such systems can spontaneously develop organized patterns. These structures are known as dissipative structures. For instance, when a fluid is heated from below, convection currents can form organized swirling patterns. Energy flowing through the system allows order to emerge temporarily from what might otherwise appear chaotic. Prigogine's work demonstrated that complexity does not necessarily violate the laws of thermodynamics. Even though entropy tends to increase overall, local regions of order can develop when energy flows through a system. Another scientist who revealed surprising patterns in complex systems was the American meteorologist Edward Lorenz. In the early 1960s, Lorenz was studying simplified computer models of atmospheric circulation. While running simulations, he noticed that extremely small changes in initial conditions could lead to dramatically different outcomes. This sensitivity became known as chaos. Lorenz famously illustrated the idea with the metaphor of a butterfly flapping its wings in Brazil and eventually influencing weather patterns in Texas. Although the butterfly itself does not cause storms directly, the metaphor captures the idea that small disturbances can grow into large-scale effects within complex systems. Lorenz's work led to the development of chaos theory, which studies how deterministic systems can still produce unpredictable behavior. In chaotic systems, long-term prediction becomes nearly impossible, because tiny uncertainties in initial conditions amplify over time. Together, these insights reveal something profound about the universe. Simple rules can generate extraordinary complexity. The laws governing particles and fields are relatively concise, yet they give rise to galaxies, planetary climates, ecosystems, and conscious observers capable of asking questions about the universe itself. From the perspective of information and complexity, physics is not only about fundamental particles or cosmic forces. It is also about the flow of information, the emergence of patterns, and the transformation of simple interactions into intricate structures. In this view, the universe becomes something more than a collection of objects moving through space. It becomes a vast network of information processing systems where matter, energy, and information intertwine to produce the rich complexity we observe around us. Even after centuries of discovery, the universe still holds many secrets. Physics has uncovered the laws governing motion, energy, electromagnetism, and the structure of atoms. It has revealed that matter consists of quantum fields, that space-time curves under the influence of mass, and that information itself may play a role in the architecture of reality. And yet, some of the most important pieces of the cosmic puzzle remain missing. Perhaps the most striking example appears when astronomers examine the large-scale structure of the universe. When scientists observe galaxies rotating, they notice something puzzling. Stars orbit the centers of galaxies much faster than expected, based on the visible matter present. According to Newtonian gravity and Einstein's theory of general relativity, the speed of these stars should decrease as their distance from the galactic center increases. Instead, the rotation curves of galaxies remain relatively flat. Stars far from the center move nearly as quickly as those closer in. This observation suggests that galaxies contain far more mass than what we can see through telescopes. To account for this discrepancy, physicists proposed the existence of dark matter. Dark matter does not emit light, absorb light, or interact with electromagnetic radiation in any detectable way. However, it exerts gravitational influence. The leading hypothesis suggests that dark matter consists of new types of particles that rarely interact with ordinary matter except through gravity. Current observations indicate that dark matter makes up roughly 27% of the total energy content of the universe. Ordinary matter, the atoms that form stars, planets, and living beings, accounts for only about 5%. The remaining portion of the universe presents an even deeper mystery. During the late 1990s, astronomers studying distant supernova explosions discovered that the expansion of the universe is accelerating. Instead of slowing down under the pull of gravity, cosmic expansion appears to be speeding up. To explain this phenomenon, scientists introduced the concept of dark energy. Dark energy represents an unknown form of energy that permeates space and drives the accelerated expansion of the cosmos. Current measurements suggest that dark energy constitutes about 68% of the universe. Taken together, dark matter and dark energy account for roughly 95% of the total energy content of the cosmos. Everything we can directly observe, from stars and galaxies to the atoms in our bodies, represents only a small fraction of what exists. Understanding the nature of dark matter has become one of the central goals of modern physics. Scientists around the world have constructed experiments designed to detect dark matter particles directly. One example is the Xenon T experiment located deep underground at the Gran Sasso National Laboratory in Italy. The detector contains several tons of ultra-pure liquid xenon. If a dark matter particle happens to collide with a xenon atom, the interaction could produce a faint flash of light and a tiny electrical signal. The detector is shielded from cosmic rays and background radiation by layers of rock above the laboratory. Despite years of careful observation, no definitive detection has yet been confirmed. Still, the search continues with ever more sensitive instruments. Another profound challenge involves combining two of the most successful theories in physics. Quantum mechanics describes the behavior of particles and fields at microscopic scales. General relativity explains gravity and the curvature of space-time at cosmic scales. Each theory works extraordinarily well in its own domain. Yet when scientists attempt to combine them, contradictions appear. For example, near the center of a black hole, gravity becomes extremely strong while quantum effects remain important. Under these conditions, the predictions of general relativity and quantum mechanics no longer fit together smoothly. Resolving this conflict requires a theory of quantum gravity. Several approaches have been proposed to tackle this problem. One of the most widely studied frameworks is string theory. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but extremely tiny vibrating strings. Each vibration pattern corresponds to a different particle. Electrons, quarks, photons, and other particles arise from different vibrational modes of these strings. String theory also proposes that spacetime may contain additional spatial dimensions beyond the familiar 3 dimensions of length, width, and height. These extra dimensions could be curled up at extremely small scales, far smaller than any distance we can currently measure. One of the most influential figures in the development of string theory is the theoretical physicist Edward Witten. Witten's work has helped reveal deep mathematical structures underlying the theory and connections between different versions of string theory. Although string theory remains mathematically rich and conceptually intriguing, experimental confirmation has not yet been achieved. Another approach to quantum gravity takes a very different path. This framework is known as loop quantum gravity. Developed by physicists including Carlo Rovelli and Lee Smolin, loop quantum gravity attempts to describe spacetime itself as a quantized structure. Instead of treating spacetime as a smooth continuous fabric, the theory suggests that space may consist of tiny discrete units. In loop quantum gravity, spacetime is built from networks called spin networks. These networks form a kind of quantum geometry in which areas and volumes come in discrete units, somewhat like pixels forming an image. If this idea is correct, spacetime at the smallest scales would resemble a finely woven structure rather than a perfectly smooth surface. Both string theory and loop quantum gravity represent ongoing attempts to reconcile quantum mechanics with general relativity. Each offers fascinating insights, but neither has yet produced definitive experimental verification. This situation highlights something important about the nature of scientific discovery. Physics is not a finished collection of answers. It is an evolving process of exploration. Every generation of scientists inherits questions from the previous one and attempts to push understanding a little further. Sometimes progress arrives through new mathematical insights. At other times it emerges from unexpected experimental results. The history of physics shows that even well-established theories may eventually give way to deeper frameworks. Newton's laws worked brilliantly until the discovery of relativity and quantum mechanics revealed their limitations. Future discoveries may similarly transform our current understanding. Yet this uncertainty is not a weakness. It is one of the most exciting aspects of science. The universe remains full of mysteries waiting to be explored. What exactly is dark matter? Why does dark energy exist? How can gravity be reconciled with quantum mechanics? These questions stand at the frontier of modern physics. They remind us that our understanding of the universe, though vast compared with earlier centuries, is still incomplete. The journey of discovery continues, and somewhere within that journey may lie entirely new principles that reshape how we understand the cosmos itself. For now, the frontier remains open, inviting curious minds to explore further and uncover the next layer of nature's hidden design.